Hello students, today we're going to be taking a look at section 6-2 entitled Exponential Functions. Our notes for today you can see, and actually this is from your textbook as well, kind of gives you a nice modeling of what is going to kind of take shape thanks to the lesson, particularly with the modeling aspect of things. It says use two pieces of 8.5 inch by 11 inch paper. Fold one of the pieces of paper accordion style for 5 folds. Fold the other in half for 5 folds. After each fold, unfold each piece of paper and count the total number of rectangular sections. So accordion style versus half. For part A, find the pattern relating to the number of folds to the number of sections for each folding style. What do you notice? Part B, make sense and persevere. Explain why the two different folded styles of paper produce different results. So this is a nice exploration of how exponential functions will take shape. After my lesson today, this is something that you can certainly attempt on your own, and then attempt also to answer on your own. Usually at the beginning of a lesson, the textbook offers something of this nature where you're kind of forecasting, I guess you could argue, how things are going to take shape. So let's go ahead and take a look. The modeling that we do will eventually lead to this type of application. So for the first example, it says key features of f of x equals 2 raised to the x power. Part A, what does the graph of f of x equals 2 to the x look like? So here's what we're going to take a look, and this is how I'm going to present things here for you today. The first thing we're going to do is highlight a table. The table and graph show f of x equals 2 to the x. So as I scroll down, and yes, this is straight from your notes or in your textbook, you're going to take notes in this regard. When you make an x-y table or x f of x, or in this case f of x equals 2 to the x table, -2, -1, 0, 1, 2, and 3. Frankly, I would argue 3 points is minimally what you'll need to graph this. If you make more than 3, like they're showing here, that's fine. But if you plug in -2 into the function f of x equals 2 to the x, you have 2 raised to the -2nd power. In terms of the math that is behind that, 2 to the -2nd is the same as 1 over 2 squared. We talked about the negative exponent property earlier, last section. So 2 to the -2nd, again, rewriting that as 1 over 2 squared, or 2 to the +2nd, leads to 1 over 4. Plugging in -1, same idea, 2 to the -1st. Okay, same here. So 2 to the -1st, 1 over 2 to the +1st, or 1/2. And then so on, 2 to the 0. Anything raised to the 0 is 1, if you remember. Plugging in 1 yields 2. 2 to the 1st is 2. Plugging in 2, 2 squared is 4. And then lastly, 2 cubed, that's 8. These 6 points are what they used. Plotting the points is fairly straightforward. There's -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. So your curve takes shape through those 6 points as such. Now, I want to make a very important connection to what would happen, let's say, if x got infinitely small, approaching, let's just say, as small of a negative number that you can imagine. If you were to plug in -3, -4, -10, -100, -1,000, and so on, if x were approaching infinity, let's just say to the left, so in other words, you're going farther and farther and farther to the left, what's going to happen here is this fraction will in fact get smaller and smaller and smaller, closer and closer to 0 technically, but never technically equal 0. That concept, as they express here, as x values approach negative infinity, y values approach 0. So you don't actually have the fraction, the y, that is, equal 0. It'll get close, but never get there. There is a characteristic that we're going to talk about more in depth. I'll allude to it now. There is imagine a horizontal line here, an invisible horizontal line that keeps that function from technically, obviously, reaching 0. So that concept technically is an asymptote. Okay, an asymptote is a very neat word. It's going to express a characteristic really of all exponential functions of this nature. The y-intercept is 1. In other words, where does the graph cross the y-axis? Well, 0, comma, and then, well, we see there 1. For part B, what are the characteristics of the graph? Well, I already alluded to the idea of an asymptote. We should also, though, note that there are other things, particularly, like I said, with the y-intercept. That's one thing, but also the fact that I said that x approaches negative infinity but also positive infinity, that's the domain of a function. I didn't say positive infinity, but gosh, if you think about it, if x gets infinitely large to the right, as you go farther and farther on the x-axis, you can have, 4, 5, 6, 100, a million. Y will still be a point somewhere way up here, and x will still be a value that we can interpret. That implies then that the domain is all real numbers in that regard. We'll also talk about range. The range is what the y's can be. For this particular function, y cannot be 0, but everything greater than 0 is an acceptable output value, we say. Inputs are x, outputs are y. On the next page, you can see the continuation of the example, and the word that I used in the context of what happens as the graph of the function goes infinitely farther and farther to the left. Well, the function gets infinitely close to 0, but not technically getting to 0. It's kind of an interesting thing. It's one of those things that applies quite nicely in pretty much every single exponential function you'll ever see. The function gets closer and closer to the x-axis, but never quite reaches it. When a function approaches a line in this manner, the line is called an asymptote. The asymptote of the function we saw up above was y equals 0, and the range, like I said earlier, is y greater than 0. The y can't equal 0, but it's always greater than 0 in that case. So let's move on to example 2. A network administrator uses the function f of x equals 5 to the x to model the number of computers a virus spreads to after x hours. If there are 1,000 computers on the network, about how many hours will it take for the virus to spread to the entire network? Okay, so you see 0 hours, here's 1 computer, 1 hour, 1, 2, 3, 4, 5 computers, and so on and so forth. So the function they give you here, f of x equals 5 to the x, is modeling what's happening after 1 hour and then 2 hours. Look at the growth, and this is an exponential growth of this particular virus spreading. Let's take a look and see, mathematically speaking, how we can attribute things. Step 1, make a table. So here's your table. Now luckily they gave you the function. Your x values are as such. 0 hours, you only have, if you plug in 0 for x, 5 to the 0 or 1 virus. So there's obviously no time passing here, and you still, as you can see, only have that 1 virus. After 1 hour, 5 to the first, there's 5 viruses. 1, 2, 3, 4, 5. After 2 hours, you're up to 25 because 5 squared, all of these computers are infected. And look at this, after the 3rd hour, we're up to 125 because 5 to the 3rd is 125 after 4, and so on. So that visual is a nice depiction of how after 2 hours things are exponentially growing. Step 2 is to graph. We have enough points to graph. Heck, minimally 3 would be fine, as you'll see me discuss and describe in later problems and aspects of videos, let's say. So with this particular function and the graph, we've got our function, we've got our points, our ordered pairs. There's 6 of them again, it looks like. So 0, 1, 1, 5, and so on. Look at the sharp increase over time. And it doesn't take long before this thing is up to over 3,000. 3,000 after 5 hours. Only 5 hours were that many computers infected. They say here when y is 1,000, x is about 4.3. So we can make that kind of assessment of values between 4 and 5 hours. So a little bit after the 4th hour hits, we're already at 1,000 viruses. So if I continue on here, the graph obviously is scaled out such that you've got what? Every 2 markings is 200 computers infected, and then every 1 is, well, just 1 hour. So there's 1 hour, 2, and so on. When you do graph on paper for your homework or for your notes, I want you to keep in mind what, in fact, these values are kind of allowing for, right? You don't want to go and make these up every 1, for example, if your highest value is 3,000. Again, you don't have to graph all 6 points. You could stop at, I don't know, 2, 25 if you've got these first 3. That should be enough to graph. But if you continue on, you're certainly going to need bigger values on the y-axis. I do also want to comment that you don't see the horizontal line at y equals 0, the asymptote, in other words, of the function. But as I said earlier, every exponential function will have, in fact, some asymptote. In this case, there's an asymptote at y equals 0. Not that you could have negative hours, but if you did have negative 1 as your x value, this function approaches 0 but never technically gets there. Step 3 is to use your graphing calculator to check to see if your answer 5 to the 4.3 in fact is close enough to 1,000, and I would argue that it is. 5 to the 4.3 is roughly 1012.91, which is close to 1,000. It will take the virus about 4.3 hours, therefore, to spread to the entire network. That's not very long. So interestingly enough, exponential functions help us kind of frame kind of theoretical situations. Speaking of the very first problem, if you guys recall, at the beginning of our lesson. So as we continue, there is a concept that what we do need to highlight here. An exponential function is the product of an initial amount and a constant ratio raised to a power. Exponential functions are modeled using the following. F of x equals a times b raised to the x, where a is a non-zero constant, b is greater than 1, and b can't equal 0. So here it is. In this particular case, they've noted that in blue, a is the initial amount, so this is what you start with. B will be the constant ratio, in other words, how this particular function is growing, or in some cases, decaying. There's a growth exponential version that we've already seen. There's also a decay exponential. Example 3. What is the written form of the function represented in the table? So let's take a look. So we've got our table. We've got our, let's say, 5 x values, and then in turn our 5 y values. If you look at the growth, and it is a growth of y, or f of x, same thing, 4, 12, 36, 108, 324. If you took 12 and divided it by the prior number 4, you'd get 3, and so on. 36 divided by 12, same value. So it turns out that the y value divided by the prior y value is always going to equal the same number. So that constant ratio of 3 will help us then dictate the equation, which in turn should generally look like this, substituting 4 for A and 3 for B, remembering that the constant ratio again was 3, but where did 4 come in? Well, that was the initial amount. If you plug in 0, you ended up with 4. So y, or f of x, same thing, equals 4 times 3 to the x power. What is the written form of the function represented by the graph? Let's take a look. Here's our graph. Okay, so we've got an initial amount of 128. Looks like, as you can see, like the last problem, we have a constant ratio, though if you take the y value divided by the prior y value, 64 over 128 is less than 1. 32 divided by 64, same ratio, but less than 1, and so on and so forth. 4 divided by 8, of course, also a half. Because the constant ratio is a half, the initial amount is 128. Here's our final equation. Put it all together in context. Of course, a is 128, b is a half. This function, y, or f of x, equals 128 times quantity a half raised to the x, is an exponential decay function model. I am going to ask that you do the remainder of the examples on your own, but please take a look, writing it down every step of the way. from your book or from my OneNote.